For an intuitive understanding of our method, we visually present our main idea in this video. Our task is to reconstruct human motion from 6 body-worn inertial sensors, which measure the real-time orientations and accelerations. Similar to previous works, we tackle this task by decomposing human full motion estimation into local pose and global motion estimation. Let's focus on the local pose estimation. By leveraging the root orientation measured by the sensor placed on the root, previous works transformed the input sensor orientations and accelerations to the root frame to estimate the root relative human pose. However, we argue that this approach is suboptimal. We show the reason by an example. Let's consider a spinning motion. The sensors on the arms should measure large centripetal accelerations due to the human's rotation, while the sensor on the root should measure very small accelerations as it is close to the axis of rotation. When transformed to the human's root frame, it results in a static T pose with large accelerations on the arms. On the other hand, if a person performs a static T pose, when transformed to the root frame, it results in a static T pose with 0 accelerations. Let's compare the results. Since the two cases have the same root relative motion, we would expect the same output for the local pose estimation task. However, the acceleration inputs differ significantly between the two cases. Furthermore, the situation becomes even more challenging when considering a retracting arm motion, which can have similar acceleration inputs to the spinning motion. However, we need distinct outputs for these two motions. Consequently, the network will encounter difficulties in learning the relationship between acceleration and human motion. The major contribution of our work is identifying and addressing this problem. In this video, we are going to explain why previous works suffer from this ambiguity, and how we solve this problem. Let's revisit this spinning motion. When static observers view the performer from their perspectives, they observe that the acceleration aligns with the spinning motion. This is the usual case. However, imagine that the spinning performer is standing on a rotating platform, and there is also an observer standing on the same platform. From his perspective, the performer is static and the acceleration does not match the motion. This is because the observers observe the performer using different reference frames. Formally, we refer to a static reference frame as an inertial frame, in which the measured acceleration always aligns with the human motion. On the contrary, the rotating frame is a non-inertial frame where Newton's laws of motion may not hold true. This explains the reason for the mismatch between acceleration and motion. In physics, people introduce additional forces in non-inertial frames, including the well-known centrifugal force and the Coriolis force, and so on. With the additional acceleration caused by these virtual forces, the human motion can be explained. To this end, it becomes clear that the human's root frame is a non-inertial frame, where the virtual forces need to be taken into account to explain the human motion. However, previous works overlooked this fact, leading to the inconsistency between acceleration and human motion. Our solution is straightforward but effective. When observing a spinning human from the root frame, the acceleration measurements do not align with the human motion. Ideally, we would expect 0 acceleration as the person appears static in the root frame. To address this, we introduce compensated accelerations to the human to explain the root relative human motion. In this example, they cancel out the measured accelerations, resulting in the expected 0 acceleration. These additional accelerations are actually caused by the virtual forces in the non-inertial frame. We formally refer to them as fictitious accelerations. Mathematically, the fictitious acceleration arises from the use of the non-inertial human's root coordinate system. It consists of 4 components. One originates from root accelerations, which is known from the sensor readings. The other three originate from root rotations, which are estimated by our method through supervised learning. With the estimated fictitious accelerations, our method effectively aligns the root frame accelerations with the root relative human motion.